Hello, my name is Andy Schweitzer, and this is one of our last videos on mass-to-mass calculations and why we use mass. Well, it turns out that if we look at most problems, or almost all problems involving a chemical reaction in atoms, let's say, for example, we have H2 plus O2 yielding H2O. Now, in this case, put a 2 here and a 2 here. These atoms are so tiny that obviously individual atoms are impossible for humans to see. And if you're picking up or counting any size that would be normal for a human being, the numbers are just astronomical as far as how many actual particles there are. So you can't really count out a mole of atoms. So turns out that for humans, any time in our daily life that we want to count large amounts of things, we use mass as a means to count. So for this point here, essentially what we do is we take a chemical, let's say for example hydrogen, and we try to figure out what's called the molar mass. Another name for molar mass would be molecular weight. So we need to have some type of relationship between the particle, okay, and its mass. Now, unfortunately, every single particle has a different number of protons and a different number of neutrons for every given element. In fact, some elements within this actual type of element, like let's say oxygen or hydrogen, they even have varying number of nitrogens, or sorry, neutrons. So these are the two things that contain mass inside an atom. So we need to find some way to link its particles, number of particles, to mass. So I can say if I have 10 pounds of hydrogen, how many actual particles are there? Okay. The definition for molar mass is the mass of 1 mole. Okay. Now, for this particular deal here, well, let's pause here for a moment. Molecular weight would be the mass of one atom, or sorry, I say one atom, or it might even be one molecule. Usually this is going to be in AMUs, but also could be considered to be in grams. So if I want to figure out the molar mass or find a link between mass and number of particles, sometimes this is called interchangeably. All you do is look on the periodic table, and let's say, for example, hydrogen. And I usually label this above the top here. Hydrogen on the periodic table has a mass of a molecular weight of 1, and there are 2 of them here. Remember, now this is the rate used. It is not involved in the actual size of the atom or how many particles are there. Different chemical reaction, hydrogen could have a different number here. Again, this is inherently how heavy the individual particles are. So there are 2 hydrogens here, so 1.00 times 2 equals 2.00, and the unit on this would be grams per mole, right? And 2 grams per mole. For oxygen, again, on the periodic table, you'll see oxygen listed. You'll have 8 protons. I don't just want the protons. I want the protons and the neutrons. That is 15.99, or I'll round it to 16. So there's 16, and that is how much one mole of the atom's weighs. So it's the average atomic mass, but it's also the mass of 1 mole of these particles. So there are 2 of them, so 16 times 2 equals 32. So 32 grams per mole. And then we have our water here. All right, again, this is the rate used right here. We don't want to include that. The hydrogen will give us 1 times 2 for 2. 16, and then just times 1 is 16. 16 plus 2 is 18 grams per mole. All right, so 18 grams per mole right here. Now, this is an important number. It allows us to make a relationship between the number of particles and the mass. So for hydrogen, it is 2 grams per mole. For oxygen, it is going to be 32 grams per mole. And for water, H2O, it's 18 grams per mole. This is going to allow us to make a linear ratio or relationship between a mass that we might weigh out and the number of moles of particles that are there. Now the moles are important because that measures number of particles. This is the mass, this is the moles, which is the number of particles. It represents how many there are. Now, why is that important? Well, it's important because in the chemical equation, things are consumed by the number of individuals. 2 of these individuals and 1 of this individual produces 2 of these. And that's regardless of how much these things weigh. Everything weighs differently. So, and mass is deceiving. So, regardless of mass, 2 of these particles, 1 of these particles, and produces 2 of these. Notice that the oxygen is 16 times heavier than the hydrogen. Yeah, it's consumed at a 2-to-1 ratio. That is important to understand. Okay. Now, if I were to start out a chemical reaction, I would be given masses of these things. Let's say I have H2 plus O2 yields H2O. All right, and 2, 1, 2. All right. I'd like to put the molar masses above them. This is going to be 2 grams per mole, 32 grams per mole, and 18 grams per mole. Just have it above here. Again, if I want to start doing some mathematics with this, okay, I would be given, let's just say, 10 grams of each of these. Okay. Now, what can I do with these grams? Well, I'm going to flip over to that page here, and before we come back to this problem, I'm just going to flip over and make a summary of our total calculation so far. We have moles, we have actual number of atoms or molecules. Of course, we know that we can use 6.022 e to 23rd things per mole, and to make that jump back and forth, that's called Avogadro's number. And from here we can also go back and forth to mass. Okay. This will use the molar mass. Because this is actually a number of particle measurement, this is a number of particle measurement, both of these guys we can do stoic calculations with. Whether it be limiting reactant, basically using our stoic ratios. Okay, the stoic ratios is this thing here, 2 to 1 to 2. So for every 2 of these, I require 1 of these, and I get 2 of those. Pretty easy to understand. The problem with that is that it doesn't mean 2 grams of this requires 1 gram of that. That is the cardinal sin of chemistry. The mass, it makes it very nice for us to actually weigh and measure things, okay? Mass is a means to count. Right here, this is a dead end. We cannot do anything with mass. I can't emphasize that enough. Mass is simply a means to count. And that's it. If it weren't for the fact these particles are so small, if we could count them individually, we would, because every single particle weighs a little different. That makes it difficult. We have some things that are bricks, some things that are feathers. In this case, for this particular chemical reaction, the oxygens have to be bricks. Hydrogens have to be feathers. If I have 10 pounds of bricks, 10 pounds of feathers, which one weighs more? Obviously, we still have the same mass, but we have a bunch more feathers, bunch more of these guys, and turns out in this case, we have lots of them. So, quick recap. How do you go about getting the molar mass of this thing? You add up the average atomic weights off the periodic table, and I'll show one more example before this PowerPoint is done. But I'm going to just show a quick calculation. How do we get this thing out of mass into moles? Well, let's do it on the side here. Okay. Now I have my hydrogen. Okay. The hydrogen has a molar mass of 2 grams per 1 mole. 2 grams per mole. So Mike, this is similar to saying you're making $50 per hour. How much money did you make? Well, you don't know because you didn't know how long you worked. This is inherently how much 2 grams is how much this number of particles weighs. How much do you have? You don't have anything. This is hypothetically, if you had 2 grams, this is how much this would weigh. Or I should say, if you had 1 mole, this is how much it would weigh 2 grams. And that's inherent from now until the end of time. Oxygen, okay, same thing except it's 32 grams. So I need one more piece of information here. Let's just say I have, okay, for this example, 10 grams. That is how much I actually have. Now I'm going to use my relationship and factor label. I could also use a ratio to flip this from grams to moles. Grams to moles. Notice grams is on the bottom because it cancels. 2 grams, 1 mole equals 2 grams. So we have 10. You should know you have more than 1 mole because 1 mole weighs 2 grams. 2 grams, 1 mole equals 5 moles. Now that can be canceled. 5 moles. A mole is something we can do our limiting and excess calculations with, not grams. For this guy, I have the same mass, but grams to moles. This guy weighs 32 grams. 10 divided by 32. Now keep in mind, 1 mole weighs 32 grams. You have 10 grams. Do you have more or less than 1? That's something I'll ask kids all the time. In your mind, what do you have? This is about a third of 32. So it is 0.31 moles. 0.31 moles. Now, it's very easy to say, okay, this is being up twice as fast. I do have more of it, but I have a whole lot more. So I'm still going to say this is my limiting reactant. Okay. From there, we'll do our limiting excess calculations, and I will show an example on a later video of a whole problem working its way through. Again, let's review this thing. I have molar mass. This allows me to measure something I can't see, all individual particles. For this, I need a relationship of grams to moles. Some amount of grams per mole. That is the molar mass. How do I go about calculating that? Let's review this. All right. Any particle that I would want to measure, I can figure out how much 1 mole of it weighs. Silver, let's go silver metal. Let's do silver nitrate. Let's do calcium nitrate. Let's do a couple problems here. Okay. How much does 1 mole of each of these things weigh? Well, on the periodic table, you can take a moment, have your periodic table nearby you, so you can kind of see where I'm getting this thing from. Silver has 47 protons. That's fine. Protons are the only thing that have mass in the atom. It's 107.87. That decimal is because of the varying number of neutrons. So it's 107.8 grams per mole. That also could be AMUs per atom. This is not as useful for us. On our life scale, we use mass. This is also a unit of mass, atomic mass unit. We'll use this one. A gram is something I can go out ahead and plug right on a scale. So I can go on a scale, grab a piece of silver, and put on there 107 grams of silver. That's equivalent to 1 mole, which is equivalent to 6.022 e to the 23rd atoms, in this case, of gold. We use the term mole to describe that number. All right, now silver. The silver, this guy is going to weigh 107. I'm going to round it off to 3 sig figs. Then the nitrogen is going to go, let's just go 0.8. Let's go to the 10th place. Nitrogen is 14.0. The oxygen is 16.0, and then there are 3 of them for a total of 48. Let's add everything up. 14, 48, 107. And this is how much 1 mole is going to weigh. 107 plus 48 plus 14, and I got 169. That is grams per mole. So if I want to weigh out 1 mole of silver nitrate, I have to weigh out 169 grams of it. That's a lot. If I want to weigh out 1 mole, half a mole, it'd be, divide that in half, it'd be only 84.5 grams. Now, let's look at the calcium. All right, the calcium has a molar mass of, looks like 40.0. 40.0. Now, there's 2 nitrogens. So I'm going to go 14 times 2 is 28. And then in this case, it's going to be oxygen will be 16 times 6. 96 grams. Add all that up. 96 plus 40 plus 28. I got a grand total of 164 grams per mole. Again, this is like saying I weigh, I make $100 an hour. You know, how much money did you make? Again, it doesn't mean anything. You have silver, 107 grams per mole. How much silver do you have? Nothing. It's just a relationship between a hypothetical silver atom and the number of particles. Okay. Now, when you're doing your calculations of these things, there's 2 things. You're either going to be multiplying by molar mass or dividing by molar mass. It's important to understand that if I have, let's just say, 100 grams of calcium nitrate, immediately, okay, you should be looking up to the periodic table and saying, well, what's the molar mass? The molar mass of this thing is 164 grams per mole. Now, it doesn't take a rocket scientist to say, okay, well, if 1 mole weighs 164, then I have only 100 grams. I have less than 1 mole. It is imperative to reduce mistakes, to do a mental calculation. I have less than 1 mole. That is very important. Okay? And in fact, you might even be able to say I have less than half a mole. But in that case, I do not. Okay? But let's do the math now. 100 grams, dot line, grams to moles. Get rid of grams, go to moles. 1 mole weighs 164 grams. So let's divide it out. And 100 divided by 164. And I have 0.609 moles. Does that make sense? Yes. 1 mole in 164, I have 100, less than 1. Not quite less than 2. All right. If I were to do just plain old silver, Ag, let's say I have 200 grams of silver. Okay. Now silver weighs 107 grams per mole. That was listed right above here. 107.8 grams per mole. I'll put the 0.8 on there. 0.8. All right. Now, do I have more or less than 1 mole? Well, if 1 mole weighs 107, I have 200. All right. Do I have more or less than 2? Well, 2. That would be 2 moles would be 214. So I don't have 2 moles. A little less than 2 moles. That calculation in your head is extremely important. Dot line, grams to moles. 1 mole weighs 107.8. And do the math. 200 divided by 107.8. The exact answer is 1.85 moles. Now, in this case, we converted a mass to a mole. Therefore, we divide by a molar mass. If we were to go from moles back to mass, it would be just the opposite. We'd multiply by molar mass. Set your units up so that your units cancel, and it will tell you whether you divide or whether you multiply. Thank you very much. This is just a simple video on mass, molar mass, and how you set it up and what it means.